Before we end this section, I would like to further elaborate on the concept of the Fermi level, EF. From the Fermi Dirac functions, it represents the energy where the probability of finding an electron in a state is equal to 1/2. In order to visualize its meaning, we'll borrow the water analogy again. Consider a very light, hollow, closed box partially filled with water. At very low temperature, the probability to find water molecule at an altitude below the water surface is equal to 1, and the probability to find a molecule in the air is close to 0. At the water-to-air interface, the probability to find a water molecule is equal to 1/2, and this is sort of the Fermi level of the box. When the material is connected to a uniform external potential, it is similar to placing the box in a water tank that the water level represents the external potential. The box will flow on the water with the water level inside and outside the box aligned. Therefore, the Fermi level is kind of a reference energy level with respect to the surrounding. When the box becomes a semiconductor, the band gap represents a solid box that no water molecule is inside. When the semiconductor is subject to external voltage, it is like dropping the solid box into a tank of water. The box will partially flow on the water, and the plane in the box that separates the floating part and the sinking part of the box represents the Fermi level of the semiconductor. However, the semiconductor is not only represented by the solid box, but also everything above and below it. It includes the water molecules below the box, which represents the valence band filled by electrons. If the solid is perfectly impermeable material, no water molecule below the box can reach the region occupied by air. However, this material is not perfect, but with cracks. Therefore, a small number of water molecules can go through the cracks to go above the solid material. This is the process how electron and hole pairs are generated. If there is a big hole drilled through the box, the water inside the hole will reach the Fermi level. Therefore, the Fermi level sort of represents the water table in the water analogy. When an external voltage is applied through a battery, the potential at the two ends of the semiconductor is changed. Effectively, it can be viewed as the battery changes the height of the external water levels. It is like the Fermi level at the two ends of the semiconductor changes. And the different Fermi levels or water levels will cause a current to flow. Some attention should be paid to here that the battery only controls the two ends of the semiconductor material. Inside the semiconductor, the Fermi level or the shape of the impermeable material depends on the properties of the semiconductor, and this will be covered later. But the motion of electrons going down the slope like water molecules and holes going up the slope like bubbles is very obvious. Please keep this picture in mind, as it will be used very often for the rest of the class to explain the dynamics of the carriers.